Okay, so I guess it's about time, and I think we will get started. Yeah, first, let me to do the introduction. Hi everyone. Welcome to attend our Optical Photonic Computing System Seminar series. So this is our fourth seminar. It will be 1 hour, including 45-minute presentation and 10 to 15 minutes for QA in the end. If you haven't registered our mail list, please scan the QR code so you can receive our emails for more events in the future. We also have Slack channel for networking and potential collaborations. Our YouTube channel is used to post past events video recording, so please feel free to share with other people to review if they cannot join online. And finally, some logistics. So the event will be recorded and we will later post it on YouTube. And if you have any question, please type it in the chat box. Jiaqi will moderate the QA session in the end, and the speaker will answer the questions toward the end of the talk. Well, so today we are very glad to invite our fourth speaker, Dr. Sanmitra Banerjee from Nvidia Corporation. So Dr. Sanmitra Banerjee is a senior design for X methodology engineer at Nvidia Corporation, Santa Clara, California, and also an adjunct faculty at Arizona State University. He received the Bachelor of Technology degree from Indian Institute of Technology, Kharagpur in 2018, and the Master and PhD degree from Duke University, Durham, North Carolina in 2021 and 2022, respectively. His research interests include machine learning-based DFX techniques, fault modeling and optimization of emerging AI accelerators and their process variations and manufacturing defects. Well, he will share with us his work titled Optimizing Silicon-Photonic AI Accelerators and their Imperfections. Well, thanks, Sanmitra, for giving us the talk, and the floor is yours.
Okay, perfect. Let me start sharing. Okay. You can see my screen, right?
Perfect. Yes.
Perfect. Okay. Hi, everybody. I'm Sanmitra. As Jenki mentioned, I'm currently working at Nvidia, but today I would like to talk about some parts of my thesis research at Duke. So this is a very interesting concept because photonic neural networks, as you might be knowing, are one of the most promising technologies beyond CMOS AI accelerators. However, there are several challenges, including like footprint, reliability. So today I'd like to point some of those reliability-related challenges. And the main takeaway from this discussion, what I would like to be is that whatever new emerging technology, either it be an accelerator or even in other cases, even for processors, we work on, like in addition to performance, power efficiency, the known PPI metrics, we should also look at reliability as one of the core performance indicators of any new technology. So I would guess that should be the main takeaway from today's presentation. So let's start. So a brief outline of what I wanted to cover today. So a background on why integrated photonic neural networks. Why did we need a new technology? And then what are the things that can go wrong in photonic neural networks? We'll explore many different issues, and we'll look at a comprehensive and systematic bottom-up approach of modeling all of these different imperfections. This will include like fabrication uncertainties, quantization errors, thermal crosstalk, insertion loss. Once we understand the impact of these different uncertainties, we'll look at how can we optimize neural networks under these imperfections. We'll propose several approaches. All of these are very, very photonic focused, and we'll discuss why conventional EDA tools that are built for silicon schemas are not just enough for photonics. So for photonics, we need new tools because the technology is fundamentally different. AI accelerators are one of the cornerstones of deep learning today. They offer variable precision, optimized matrix multiplication. However, one of the challenges is a huge energy efficiency gap. So The best processor that we know till today is the human brain. And if we compare the energy efficiency of the human brain to, let's say, an Intel CPU, it's around 6 orders of magnitude less energy efficient than the brain. With Moore's law, with CMOS scaling, that gap can be brought down by 10x. Then with parallel computing, GPUs, AI-specific hardware, that can be brought down by another 100x. But the question still remains, how do we bridge this 1000x gap in energy efficiency that still remains? And in the past few years, there has been a renewed interest in exploring accelerators based on emerging technologies that can be photonics, that can be carbon nanotube FETs, that can be RDRAM. So these emerging technologies show significant promise in bridging this gap. Silicon-Photonics is particularly interesting because here the computation happens in the optical domain. So matrix multiplication is highly parallelized, happens at the speed of light, and is in principle constant time. And if you look at the two constituent domains, one is photonics, one is CMOS, both of them have their own advantages and disadvantages. But Silicon-Photonic merges the advantages from both of these domains. And if we look at comparison of Silicon-Photonic AI accelerators with existing state-of-art AI hardware, we'll see that footprint efficiency-wise, we have a satisfactory footprint efficiency. However, there's still some work needs to be done to make sure that we can go from this point where we are now to this point where we have around 100 teraMAC operations per second per millimeter square of footprint and a sub-femtojoule energy overhead per MAC operation. So while things are looking promising, not all things are there are, of course, two sides of a coin. So there are several challenges that would be the focus of the presentation today. But before we go there, let's give a brief overview on what are photonic neural networks and how they work. So there are two main domains here. One is coherent photonic neural networks, one is non-coherent photonic neural networks. So in coherent photonic neural networks, we work with a single wavelength, whereas in non-coherent, we can work with a range of wavelengths. There are advantages and disadvantages to both. For the purpose of today's talk, I'll focus on coherent photonic neural networks, which are based on Mach-centered interferometers. I'll cover all of these details soon. So if we look at a neural network, essentially, let's consider a fully connected neural network. These are cascaded multipliers. So multipliers followed by a nonlinear activation, then a multiplier followed by a nonlinear activation, and finally ending at some kind of a pooling layer, like a log softmax. Now, using singular value decomposition, any matrix, any generic weight matrix can be decomposed into a product of a unitary matrix, a diagonal matrix, and another unitary matrix. So if we look at this particular layer here, we can decompose that into LM, the weight matrix corresponding to this layer can be factorized into U times sigma times V Hermitian. So U is a unitary matrix, V is a unitary matrix, sigma is a diagonal matrix. And each of these three matrices, the two unitary and the diagonal matrices, can be represented by devices called Mach-centered interferometers. So these are interferometers with two phase shifters and two beam splitters. We'll have a diagram of that coming soon. But basically, these are interferometric devices. They can represent any unitary and diagonal matrix. And in turn, by having a product of unitary and diagonal matrix, they can represent any weight matrix. So for example, here, if we have a 4x4 unitary matrix, it can be represented by 6 MZIs. So each of these oval-shaped, grayish oval-shaped structure is 1 MZI. And an n-cross-n diagonal matrix can be represented by n MZIs. So in total, for a 4x4, we need 6 MZIs for the unitary part, 6 MZIs for the other unitary part, and 4 MZIs for the diagonal part. So let's take a look under the hood, what is there inside these MZIs. So as we discussed before, for an n-cross unitary matrix, we need n choose 2 MZIs. And each MZI consists of two main components, phase shifters and beam splitters. So here we have two phase shifters with a phase shift of theta and phi, and two beam splitters within this dashed circles. So in each phase shifter, we basically, the optical signal going through the waveguide is applied, like some phase shift is applied to the optical signal going through that waveguide. There are different ways of applying this phase shift. We can use like PCM materials. We can use thermo-optic effect of silicon. So for our research, we have primarily focused on thermo-optic phase shifters. But again, just wanted to clarify that there are other ways of doing this. So basically, the way it is stored in memory, then the stored digital weights are converted into an analog input to the voltage driver. And whatever voltage is provided to the heater coil, the resultant phase shift is directly proportional to the square of the voltage. The other component are the beam splitters. So these are passive components. So each beam splitter transmits a part of your optical signal to the other waveguide and reflects a part of the optical signal to the original waveguide. So again, this is a passive element, so we do not tune the beam splitters. All we do during training is that we tune these phase angles to minimize the loss. So this is an analog of a weight parameter that we have in like software-based neural network training. Now there can be several imperfections. So there can be nanometer scale lithographic variations. For example, the waveguide width and thickness might change. The length of the phase shifters might change. There might be thermal crosstalks if you have multiple MCIs close to each other. And because we are using the thermo-optic effect, so the temperature, like a thermal hotspot might build up if you have too many phase shifters that need a high temperature, like a high phase shift. And that might lead to thermal crosstalk to another victim phase shifter that whose phase shift might change due to these cross thermal effects. There can also be insertion losses. So MCIs are lossy devices. There can be coupling losses. There can be propagation losses. There can be absorption losses. We'll talk about these losses a little more later. And finally, as is true with any neural network, there can be quantization errors. So if we want to reduce the memory overhead associated with storing the weights, we will inevitably incorporate some quantization errors, and we'll see that the effects of these quantization errors is different based on which MCI, like which phase angles are quantized. Now, we have identified these different imperfections, right? And this is in no way a comprehensive list. So these are just some effects that we studied. There are many other things that can go wrong. And again, the focus the focus today is not about giving a laundry list of all the things that can go wrong, but I just wanted to present that if we know what are the things that can go wrong, where do we go from there? How do we quantify their effects? And how do we build methods that can either reduce the effect or can totally bypass those effects? So the first step towards that is building a bottom-up modeling framework. So let's say these are the effects that we had identified before: phase shifter and beam splitter uncertainties, quantization errors, insertion losses. Then these phase shifter beam splitter uncertainties can arise due to fabrication process variations. They can arise due to thermal crosstalk, due to manufacturing defects. Quantization error can arise due to, like, if we want to use low power DACs, if we have memory constraints to store our trained weights. Insertion loss can arise due to fabrication process variation, absorption loss in the microheaters, propagation loss in the waveguides, coupling losses, and so on. So the first step towards studying these is to come up with parameters. So for example, phase shifter and beam splitter uncertainties can be measured by assuming a standard deviation. So what if all our phase angles are not perfect? What if all our splitting ratios are not perfect? Quantization error can be quantified by using the number of bits that we use to store the phase angles or the inputs to the voltage driver. Insertion loss can be used by considering that we have a mean background loss across all the MCIs, and then we have a spread across all the MCIs around that background mean loss. Once we have the parameters defined, we should start from the bottommost level, which is the component level. So at the phase shifter and at each individual phase shifter and beam splitter level, how do these parameters affect our phase angles? How do they affect the splitting ratios of the beam splitters? This in turn, how do they affect MCI transfer matrix at the device level? So imperfect phase shifters and beam splitters will lead to imperfect MCIs. And here we'll also include the effects of the insertion loss parameters that we had. Then imperfect MCIs will lead to an imperfect MCI array. So whatever unitary transforms we want to represent with this MCI transfer matrix, MCI array will now be faulty. And finally, a faulty MCI array will lead to faulty matrix multiplication and will therefore lead to loss in the inferencing accuracy. So if we start at the first level, which is component level, so of course we are considering thermo-optic phase shifters. So changes, lithographic variations in the phase shifter length, or changes in the temperature due to thermal crosstalk or due to low precision drivers can lead to variations in the phi, which is the phase angle. So prior work has shown that even in mature fabrication processes, on an average 0.21 radians of average error in phase angles is expected. Of course, this can be much higher for immature fabrication processes. Even for beam splitters, on an average, even for mature processes, a 1 to 2% deviation from the 50-50 splitting ratio is expected. But again, all these numbers are for like very stable mature processes. If we are bringing up a new chip or a new accelerator architecture, all of these numbers will be much higher. So let's take a look at the device level. So at the device level, the MCI transfer matrix is given by this equation. So we have the theta and phi at the two phase angles. And in the presence of uncertainty, we can have like the transfer matrix TMCI can change to T tilde. And we use the fidelity, which is defined as follows, to measure how much the deviation is. So if we look at if we look at MCIs with different phase angles, so we have theta and phi phase angles. And if we look at if we insert relative variations like 1%, 5%, 10% relative variations, the topmost contour is for 10%, the fidelity decreases. So just note that this axis is 1 by fidelity. We use this for ease of plotting. So fidelity goes down and 1 by fidelity goes up as you have MCIs with higher theta and higher phi phase angles. So this shows that not all MCIs are equally susceptible to uncertainties. MCIs with higher phase angles and higher theta and phi phase angles are more susceptible to uncertainties than MCIs that have phase angles pretty close to 0. And as we'll see later, this will be a very nice motivation for us to try out model compaction or pruning approaches for photonic neural networks. So this is where that motivation comes from. So a higher phase angle means that our network is more susceptible to uncertainties. From the device level, if we go to the layer level, when the transfer matrix of an MCI deviates, the unitary matrix itself changes. The unitary transform that we are realizing with this MCI array, that itself changes. So we use this relative variation distance as a measure of like what is the difference or distance between the actual and the expected unitary transforms. And we see that again, if we try different unitary matrices, so here we have 4 different 5x5 unitary matrices. 5x5 unitary matrices need 10 MCIs as shown here. So across these 4 different 5x5 examples, we see that different MCIs are critical in different cases. So for example, for U1, the maximum average variation distance was observed when there were variations in MCI number 2, which is this MCI. For U2, the most critical one was MCI 8, which is this MCI. So what this shows is that the criticality of photonic neural network components is highly tied to the tuned phase angles. So it's very difficult to do a criticality analysis if we do not have a trained network already. So in other words, the criticality will be very, very dependent on what kind of workloads and what kind of tasks we are doing. So that is one of the main challenges in including any kind of protection or redundancy measures, particularly for general purpose hardware, because if you're running different workloads on the general purpose hardware, different components will become more or less critical. So from the layer level, if we go to the system level, so where so first we started as phase shifters, beam splitters. Imperfect phase shifters, beam splitters led to imperfect MZIs. Imperfect MZIs led to imperfect unitary transforms. And finally, imperfect unitary transforms will lead to imperfect matrix multiplication and a fall in the inferencing accuracy. So we intentionally chose a very simple task here. We just chose the MNIST handwritten digit classification task. And we also chose a very simple network. So this is just an MLP with 2 hidden layers and 3 multipliers. So in between, like the first layer, input layer, and the hidden layer, we have 1 multiplier. First hidden layer, second hidden layer, we have the second multiplier. And second hidden layer and the output layer, we have the third multiplier. So with just 3 multipliers, we were able to get like close to 94% accuracy, which is again expected because this is a very simple task. But the interesting point here is that even under expected levels of uncertainties, even when we have a 5% standard deviation, we see a huge drop in accuracy, like a 75% drop in accuracy when we have just a 5% standard deviation in both phase shifters and beam splitters. Of course, 75% accuracy drop, like at this point, the network is useless, right? So in today's case, even a 5% or a 10% accuracy drop is not acceptable, right? So somewhere around here, even with a 1% standard deviation, we can see a close to 10% accuracy loss. So this shows that these random uncertainties in phase shifters and beam splitters really are very crucial. And we need to find out ways to counter this because this is not acceptable. This is not acceptable for a task like MNIST, right? So you can guess that for more complex tasks, of course, the network will struggle in the presence of these kind of uncertainties. Photonic uncertainties can also be spatially correlated. So before we were only looking at uncorrelated uncertainties, but there could be cases where they are spatially correlated. So for this, we take a variation map and we apply a Gaussian smoothing filter on top of it with different correlation lengths. And we try to simulate the case of a correlated, spatially correlated variation map. So here you can see that MZIs that are close together have similar levels of imperfection. Also, there can be cases where there can be radial dependence. So particularly in silicon wafers, it is well known that dyes towards the edges of the wafers are more more imperfect compared to dyes towards the center of the wafer. So to mimic that effect, we also started with a radial variation map. To apply spatial correlation, we passed it through this Gaussian smoothing filter, and we obtained a radial and spatially correlated variation map here. So these are just some examples. We tried out different correlation lengths, different standard deviations and uncertainties in phase shifters, standalone beam splitters, standalone in both phase shifters and beam splitters. So a highlight of some results here. So this plot shows on the x-axis, we have the standard deviation of the phase angles in the phase shifters. On the y-axis, we have the inferencing accuracy. And each line denotes different correlation lengths. So higher the correlation length, higher is the degree of spatial correlation. And the blue line denotes when we do not have any correlation. So we tried these for different cases. So this is for phase shift uncertainties in phase shifters with non-radial variations. We have a radial version of that. We also have beam splitter, non-radial and radial. We also have both phase shifters and beam splitters, non-radial and radial. So this is a bit busy slide. I know there are too many charts here. So let's just go over the main takeaways. So the first takeaway is that we see that from the no correlation case to the high correlation case, across all these different scenarios, the inferencing accuracy drops more as we go to more correlated uncertainties. So which says that for the same standard deviation, we would rather have uncorrelated variations than correlated variations. Correlated variations have a much more catastrophic impact than uncorrelated variations. And which is in a way intuitive, right? Because if you have large correlated uncertainties, that means a huge fraction of your devices have variations in the same direction. Whereas you have uncorrelated and highly randomized variations, that means there is a chance that variations between different MZIs can cancel out. So the main takeaway again is that we would rather have random variation than highly correlated systematic variation. as we also discussed, MZIs are lossy devices. So, and these losses can be non-uniform. So due to variation. So one example of loss can be losses in the beam splitters. So ideally we would have a reflectivity and a transmittivity ratio of 1/√2, 1/√2, which means half of the signal power is transmitted, the rest half is reflected back without any dissipation. But in the presence of coupling losses, absorption in the microheaters, waveguide propagation losses, this 1/√2 ratio can change to beta/√2, where beta is less than 1. So we model this like by adding this loss function to the MCI transfer function, and for this loss function to introduce non-uniformity in this loss function, we also assume that that loss function also has a spread. So there is a mean background loss across all the MCIs, and also there is a spread. So as you'll see in the results, this spread also matters. So even if you have a background loss, even if you have a constant background loss, for example, in this case, the blue line here. So here the x-axis is the sigma IL, which is the spread, the standard deviation. Y-axis is again the inferencing accuracy. So we see that for all of these 4 lines, we have the average background loss is 0. But as the spread increases, our inferencing accuracy goes down quite significantly. So this non-uniformity in the insertion loss is also quite catastrophic while inferencing. Another interesting effect here is that, remember that we talked about that we had 3 multipliers. So we had 2 hidden layers and we had 3 multipliers. Input hidden layer is 1, hidden layer 1 is 1 multiplier, hidden layer 1, hidden layer 2 is the second multiplier, hidden layer 2 and output layer is the third multiplier. So here we wanted to see how do losses in each of these individual multiplier layers affect our inferencing accuracy. And we see that L0 is the first layer, right? So a loss in the first layer have much higher impact than loss in the last layer. So as we go more towards the output, it seems that the network becomes more and more resilient to insertion losses. And this is a theme that we'll see repeating again and again, even when we go into like quantization errors, when we go into pruning, we'll see that like in at least in coherent photonic neural networks, we see that earlier layers are more susceptible to any kind of imperfection. They can be pruned less. They are very susceptible to loss. They're very susceptible to quantization errors, whereas later layers are more resilient. So a design choice can be that if we know that some of our MCIs are imperfect, whereas some others are quite close to ideal, it would be efficient if we could use the ideal MCIs, map the ideal MCIs to the earlier layers, and use the more imperfect MCIs to the later layers, because the later layer parameters seem to be more resilient to these kind of imperfections. Finally, we'll look at the last imperfection, which is the low precision phase encoding. So recall that initially our weights are stored in the memory, which are converted using a DAC as analog inputs to the voltage driver, and finally the voltage is converted to the phase change due to the heater coil is directly proportional to the square of the voltage output. If we do low precision encoding, that will help in reducing our memory overhead, that will help in reducing the DAC power, but that will lead to a higher quantization error. So we wanted to analyze the effect of this quantization error, and we developed 3 different ways or 3 different paradigms of quantizing our photonic neural network. So one is an equidistant voltage step. So let's say we know that our voltage range to realize the 0 to 2 pi is between 0 to V1, and we want to check 8-bit quantization. So we'll segment this 0 to V1 range into 256 different 256 steps. The other approach is equidistant phase steps. So here we segment the 0 to 2 pi phase range into 256 different steps if we are looking at 8 bits. And the third is k-means clustering, where we look at the distribution of the phase angles in our current photonic neural network, and we cluster them into 256 different clusters for 8 bits. For n bits, we cluster them into 2 power n different clusters, and we just use the cluster centers as a representative of all the phase angles in that cluster. So across all the three cases, equidistant voltage step, phase steps, and K-means clustering, we see that beyond 7 bits, like 7 to 8 bits, that we reach the maximum possible accuracy. But more importantly, even a 1-2 bit degradation in the, like, even if we quant from 7 to 6 itself, we see a large drop in the inferencing accuracy, and that drop keeps on widening as we go to lower number of bits. Another interesting trend across all the three paradigms is that, again, layers that are closer to the input, so in this case L0, the orange line here, are more sensitive to quantization errors. So the inference accuracy drops steeply if we just quantize the L0 layer compared to the L2 layer, which is the third layer that is closer to the output, where still the drop happens, but it's much less compared to the earlier layers. So again, this is that recurrent theme that earlier layers seem to be more prone to any kind of uncertainty. If we compare these three approaches, we see that the K-means clustering approach has a lesser drop, but in my opinion, like in all the three cases, the drop is very, very significant. Like in K-means clustering just gives us like one extra, like saves us one extra bit. Like in 6 bits, we can get the same accuracy as what we get with 7 bits with the other methods. But the main takeaway here should be that it's like the networks are very, very sensitive to quantization errors, particularly the devices in the earlier layers. So across all of these cases, we have observed that phase shifts are very, very, like if we have any change in phase shifts, either be due to process variations, due to quantization errors, due to losses, due to thermal crosstalk, due to whatever reason, if our phase angles change, our inferencing accuracy drops by a lot. So that's why to counter these imperfections, we decided that why don't we try out pruning? If we can prune and if we can remove most of the redundant phase angles from our network, that will help us in reducing the number of sensitive components, right? So in addition to helping us reducing the power consumption, in helping us reducing the footprint. So this is particularly crucial. Pruning is particularly crucial for photonic neural networks because phase shifters have a large footprint, and this is one of the main challenges of coherent photonic neural networks, that like these are hundreds of microns large, where we are looking at like a few nanometers in silicon. We cannot afford such large devices in photonics, and the number of phase shifters increases square of the number of bits of data. Moreover, the tuning power is directly proportional to the phase angle, and this tuning power is a constant power that we need to provide during inferencing. So if we can reduce the phase angle, this will be a savings throughout the entire life of the part. So like it's not just a one-time saving in power, not just a saving during training, but during inferencing, if we can reduce the phase angles on an average of 50%, that will translate to a direct 50% savings in power. And also, as we also saw before, that high phase angles are more susceptible to uncertainty. So if we prune, we see that the accuracy loss decrease, like the dashed line here denote the accuracy loss with the lower phase angles, MCIs with low phase angles, and the solid line denotes MCIs with higher phase angles. And we see that the accuracy loss decreases significantly if we can prune if we can prune at least some of the phase angles, and we'll look at this result in more details in a bit later. The summary is that pruning phase shifters is essential to the scalability of photonic neural networks. However, there are challenges. So in deep neural network pruning, this is a very, very well studied field. So one of the very nice approaches is to clamp small weights to retrain the rest of the weight and to obtain a sparse weight matrix. We can do this iteratively. There are several methods of scheduling these pruning steps. The challenge is that a sparse weight matrix does not always correspond to a sparse phase angle. So let's say even if you have a 95% or even a 99% sparse weight matrix, like a software weight matrix, when you map this weight matrix to your hardware, your photonic hardware, to your MCI array, it doesn't guarantee that the MCI array will be sparse. So I'll just bring your attention to the outer plot here. The inner plot is just a special case of that. So here we have matrices, software weight matrices that are at least 80% sparse. So somewhere between 80 to 100% sparse. And when we map these weight matrices to photonic domain, we see that in many cases, like the sparsity of phase shifters is still very small. So this is a histogram showing for how many cases we have very like low sparse phase shifters in our MCI array, and we see that there are a lot of cases where the phase shifters are not sparse at all, even though we had 80% sparsity in the weight matrix. The insert just shows the same for 95% case, and even with 95%, you see that particularly for the larger weight matrices, the 256 cross 256 weight matrix, even if this 256 cross 256 weight matrix is 95% sparse, in so many cases we have that the resultant weight matrix, the resultant MCI array is not sparse at all. And the reason for that is there is a bidirectional many-to-one mapping between the weights and the phase shifters. So let's say we have this 5 cross 5 array, and we have this 10 array with 10 MCIs. The number in each cell here denotes which MCIs controls that particular element of our unitary matrix. So for example, in this case, all of these 6 MCIs, like the phase angles in all of these 6 MCIs affect these particular weight matrix element. So this is the many-to-one mapping in one direction. Similarly, we have a many-to-one mapping in the other direction too. So a single MCI, phase angles in a single MCI can affect multiple matrix elements, multiple weight matrix elements. So due to this bidirectional mapping, it's very difficult to prune our software weight matrices in a way that when we map them to hardware, they will remain sparse. So software pruning of weight matrices does not really reduce overhead here. So for that, what we need to do is hardware-aware pruning. So the pruning aim should be sparse phase angles and not sparse weights. We do not care so much about whether the weight matrices themselves are sparse, but we want, when these weight matrices are mapped to the hardware, then the phase angles should be sparse. Hardware-unaware software pruning does not really work. So prior work has shown that only somewhere around 30% of phase shifters can be pruned. If we do not look at the photonic hardware at all and just try to map software pruned weight matrices back into hardware. So coherent hardware-aware magnitude pruning, shortened to CHAMP, is the first effective pruning method for photonic neural networks. Here we implemented photonic training. So we do backpropagation on the phase angles themselves and not the weights. And we iteratively clamp the phase angles themselves and not the weights. So in essence, the idea of this work is very simple, and it's very similar to what we have for software pruning, but with a key difference in that instead of pruning the weight matrix elements, we prune the phase angles below a threshold, we clamp and we retrain. Rest of the steps are very similar to what we have for DNN pruning. So we start with an unpruned neural network. We launch multiple parallel pruning runs with different pruning rates. We clamp, we retrain, and we obtain multiple different pruned models. And out of these multiple different pruned models, we see which one has the highest sparsity while still ensuring that our inferencing accuracy lies within whatever threshold we have defined. We identify that best model. So this part is the one-shot part. So in one fell swoop, we just try to prune the models at different rates. Let's say this branch can be like we prune the top 10%, the bottom 10% weights, we clamp them all to 0. This can be bottom 20%, 30%, 40%, and so on. So this is just a very crude one sweep method to prune as much as possible quickly. So this is the one shot part. And now that we have the one shot prune model, we then slowly, with a very low granularity, we increase the threshold a little by little. So, and then prune iteratively, clamp iteratively, retrain iteratively, and we iterate this loop slowly so that we can improve sparsity while not reducing our inferencing accuracy by too much. So these are essentially just scheduling details, right? So the main theme is just this. So instead of pruning weight matrices, prune the phase angles, clamp and retrain. So this is basically the iterative flow. So if you look at the simulation results with 2 hidden layers, again, these are very, very small multi-layer perceptrons with only 16 neurons each, total 1300 phase angles. We wanted to show that even if we have a very small network to start with, we can do, like, we can still prune a lot of phase angles out of these 1300 odd parameters that we have, simply by changing from pruning the weight matrices to changing the phase angle, to pruning the phase angles themselves. So we have these 2 flavors. One shot is fast and parallelize the initial steps. Then we have iterative, which is gradual and low accuracy loss. And these are the results showing the inferencing accuracy, the sparsity of the phase angles, and the mean phase angles in radians. So again, a bit busy chart. So let me just walk you through it. So initially, we have very less sparsity. We have whatever mean phase angles we obtained after training. This is shown by the green line here. And we have high inferencing accuracy. So with one shot, which is a more crude approach, we see that the accuracy drops quite quickly. For this work, we assumed a 5% accuracy loss because this is a very small network to start with. With 1%, we didn't see much sparsity. So we considered 5% accuracy loss. I'll also have results on 1% in the next few slides. So with a 5% accuracy drops quite significantly, and we could only achieve around 31% sparsity. But with the iterative approach, which is a bit more fine-grained and iterative, we have more retraining epochs there. We could achieve up to a 55% sparsity, again, on this network that was very small to start with. If we take this up a notch to a very large network with around 170K parameters, by parameters I mean phase angles, we see that if we compare the histogram of the phase angles in the unpruned case, which are these red bars here, to the iterative case, which are the green bars, we see that most of the phase angles now lie within the first bin. Like most of them are either 0 or very close to 0. And just some numbers here for this larger network with a 1% accuracy loss, we could prune up to close to 99% phase angles, and this led to a direct reduction in power savings by around 97%. So in the interest of time, I'll just, I had a few more slides on pruning, so, but I also want to have a discussion. So I'll just quickly go over the next few slides. So the other approach that we developed was regarding lottery ticket hypothesis. So this was an improvement on the magnitude pruning case. So lottery ticket hypothesis, I'm sure you're familiar that this was a paper that proposed that every neural network has a small subnetwork within itself that can be trained very quickly and can achieve at least as much accuracy as a larger network if trained in the right way. And they proposed that after every round of pruning, we should reinitialize the we should put all the unpruned weight values back to whatever initialization we started with. So basically, the basic principle is the same. In every round, we prune some bottom K percentile of the phase angles. But instead of retraining from there, we first reinitialize the remaining non-zero weights back to their initial value and again start retraining. So this takes we observe that while this takes a few more rounds of fine tuning because we are always reinitializing back to its original value, but we are achieving a much higher sparsity. So in the interest of time, I'll not cover the flowchart in details, but basically this is exactly what I discussed in some details. The main step is this one here. So all of these are just some loops where we check whether we have acceptable sparsity or accuracy. But the main step is this one. So instead of, after updating the binary masks to make sure the unpruned weights are not updated, we after updating that, after updating the binary mask to make sure that the 0 weights are not updated, we restore all the initial weights to their original, like all the unpruned weights to their initial value. That is essentially the main difference here. And doing that, we see that again, we have two different flavors here. One is layer wise, where we prune some fraction of weights from each layer, and we have a global flavor where we prune some fraction of weights globally. So let's say 20% fraction globally versus 20% in each layer. And we see that with layer-wise pruning, we can now achieve up to an 89% sparsity on the same network, where we stopped at 55% with just simple magnitude pruning. With global, the number is the global is a bit underperformed. It's still around 57%. The reason for that is with global, we are seeing that the earlier layers very quickly have a very high sparsity, because here some layers may have very large sparsity, some layers may have very small sparsity, but due to how the weights are distributed, the earlier layers were getting pruned quite often than the later layers. And as we have seen before, earlier layers are very, very sensitive, right? So we could only go up to 57% sparsity before the accuracy started to drop. Looking at the histogram, again, we see that similar results before pruning, which are these red bars, a widespread distribution of phase angles. But after pruning, we see that most of the phase angles lie either at 0 or very close to 0. If we also compare these different approaches, we see that magnitude pruning is good for some baseline pruning where we can only afford less than 1% accuracy loss. But for high sparsity, we need to use layer-wise lottery ticket hypothesis-based pruning. So if you can afford up to 5% accuracy loss for these small networks, we can get like close to like 89-90% accuracy. So here, for example, here we have almost 89% accuracy with a 5% accuracy loss, 89% sparsity with a 5% accuracy loss. Also, in the presence of uncertainties, we saw that if we simply power gauge the pruned phase shifters, there is not much difference. So here the x-axis is the standard deviation of the phase shifter uncertainties, y-axis is the inferencing accuracy. So both the unpruned and pruned networks perform similarly if we simply power gauge. This is because those devices are still there in the network, just that their phase shifts have been turned to 0, but under these uncertainties, it deviates from the 0 value, and as a result leads to accuracy loss. But if we can remove the pruned phase shifters, which will first of all help us in improving the area, we also get a much higher accuracy under imperfections. So we see that there is still an accuracy drop. So in no way are we saying that simply pruning will solve all our problems, but they reduce the level of the impact that these kind of imperfections can have. So removing pruned phase shifters improves reliability. And finally, we also wanted to explore a method where we use a hybrid flow of both lottery ticket based pruning and magnitude pruning. So lottery ticket based pruning is slow but effective. Magnitude pruning is quick, but we can't get as much sparsity there. So in this hybrid approach, we just use the first few rounds of magnitude pruning to quickly ramp up the sparsity to some moderate level, and then we use fine-tuned lottery ticket based pruning to improve the sparsity further. So as a result, we see that with hybrid prune, with only around 52 fine-tuning epochs, we can get close to 86% sparsity. Compared to if we had just used lottery ticket hypothesis-based pruning, we would need almost 5x of that epochs to get similar levels of sparsity. So this is particularly useful for in-field. So if we cannot spend too much time in pruning and we have received some new workload due to which we need to quickly prune the network and power gauge some of the MCIs, this can be an approach that can help in reducing the time overhead associated with pruning. I'll finish with some key takeaways. So photonic neural networks offer ultra-fast, low-energy matrix multiplication. We saw that correlated uncertainties in phase shifters and beam splitters are more critical than more random uncertainties. MCIs in the initial layers are more critical. They are very, very sensitive to uncertainties. Mitigative techniques should target phase shifters, particularly phase angles. Pruning improves our reliability, reduces power consumption, reduces footprint. And most importantly, pruning for photonic neural networks must be hardware aware. So again, while all of these emerging technologies show a lot of promise in terms of performance, care must be taken to study their reliability, like give as much importance to reliability as we give to, let's say, energy efficiency or performance. Finally, I would like to thank my collaborators. This work would not have been possible without Professors Madhi Nigdas and Sudeep Pasricha from Colorado State University, Fort Collins. I also would like to thank my advisor, Professor Chris Chakraborty. Amin was a student who helped me a lot during this research, and I'd also like to thank DARPA and NSF for funding my PhD thesis. Thank you, and I look forward to your questions.
Yeah, thank you very much for the great talk, especially the very detailed technical discussion on the phase errors for photonic neural network. Indeed, robustness is critical for the practical deployment for AI accelerator. And indeed, you can see the problem is super unique for photonics, right? It's not like a general problem among all the analog accelerators. So just next to your pruning type of work, is there a quick question? What type of value you want to prune your phase shifters to? Actually, if you prune the phase to a multiple of 90 degrees, 0, 90, 180, you can cancel the MZI structures, right? For example, 0 is a crossing, pi phase shifter is a bar. So is there any preferred value?
So for now, because we were considering thermo-optic phase shifters, we pruned everything. We tried to bring everything as close as possible to 0. So even for 90 degrees, we are not looking at changing the structure of the MCIs themselves. So even a 90-degree phase shift would need some power to maintain it at 90 degrees. So for that, in this work, we kept it, we assume that we want to keep it as close as possible to 0. But I agree with your point that if you can afford to change the structure of the MCI themselves for let's say a very special purpose AI accelerator that we know that will always be used for one particular task, then it makes sense to like push it closer to multiples of 90 degrees. But then again, if it's a general purpose accelerator, then you need either some sort of remapping where you need to have all different types of MCI structures present and remap on the fly.
Yeah, you can indeed make it general by setting the bias to be 90 degree, right? You can create a little detour on the waveguide such that applying 0 volt, the MZI is 90 degree. Yeah. So probably they cover different space, right? Prune to 0 versus prune to 90 degree. Probably the matrix cover different space. So probably there is some difference on the accuracy they can maintain. That's my assumption. Okay. I didn't follow the order in the chat box because I feel like I can cluster some questions. For example, also a question related to pruning from Hanqing. Since your pruning aims to saving area by removing phase shifters, does pruning hardware by removing phase shifters make the MZI non-generalizable? I think I already answered this question, right? You just do a power gating, not removing the phase shifter. Yeah, indeed. Yeah, if you didn't remove the phase shifter, only power gating is still general, right? Still universal optical linear units. Okay, another question also related to pruning. Compared to pruning, right? So it pruned the MZI because you customize to a certain task, right? If you change the task, you need to re-prune it, right? A generic way to handle the non-duality is to insert some monitors, insert some tunable structures, so you can 100% calibrate those errors. So is it possible, or is it worthwhile, considering cost efficiency, to have a circuit design that is immune to all the errors with those error correction structures?
Yeah, that's a great question. So I totally agree that pruning is very specific to a task, and it would be better to have some other, like if you're just looking at correcting errors, it makes sense to have other error correction measures. So in a prior work, we looked at, can we counter the effect of insertion loss by having intermittent like gain blocks, right? Also, there are some sensors, like I think there's some papers on capacitive sensors that can measure like errors in your optical signal powered at different points. Yes. So if our aim is to just have just to make our designs immune to errors, then pruning might not be the best approach. But countering errors in addition to saving power, particularly for very power hungry applications like thermoptic phase shifters, there I think pruning makes sense.
Yeah, thank you. Then I'll go back to the first question. For page 4, I also have this question. So what does this O1 mean for time complexity or something for the matrix multiplication complexity?
Right. So if you think of how does the matrix multiplication complexity, like the time of a n cross n matrix multiplication scale, right? So typically the depth, like if you, let's say for n becomes 2n, the depth of your MCI layer will increase, right? So, but the optical signal propagation through like the time that the optical signal takes to propagate through this entire depth, that will also go up, but because it's happening at the speed of light and at like, so therefore that the increase in delay won't be much noticeable. So like if your matrix multiplication scale goes up, it's almost constant time. Like your area overhead will of course increase by much, or if you want to do like you don't want to use the same hardware for multiple parts of computation, then your time will go up. But if you can afford to not, if you can afford as much hardware as you want, it's really the time is the time is just how much time the light signal, optical signal takes to propagate from the input to the output, right?
Yeah, so intrinsically it should be linear to the matrix size, right? Even its light speed, because the circuit depth is linear to n.
That's a good point. But I feel that like in terms of the delay, like the actual measure of the delay is so small, it's like it's non-existent. But yeah, I think you are right. Like if you like, yeah, mathematically it should be linear. Agreed.
Yeah. So if the light propagation delay is shorter than your clock cycle, everything can happen within clock cycle, so it's constant.
Right.
But think about the 1000 by 1000 matrix. You will trigger the error constraint before you trigger the time delay constraint. Yeah. Okay. Another question from Zhengqi. I heard the thermal optic phase shifter has slow response speed. Take a while for the phase shifter to achieve desired phase shifter, so the thermal constant time is quite long. Would it have any problem for the photonic system with those slow thermal phase shifters?
Yes, that's also a very good point. So yeah, this is a known issue with thermoptic phase shifters in addition to several other known issues. When we started this work, thermoptic phase shifters were something that people were exploring with interest, but yeah, now all of these new issues have come up. So recently people have started using like phase change memory, like phase change material based like ways to impose phase shifting using PCM materials. So I feel thermoptic phase shifters are not very scalable, and this is definitely one of the reasons for that. Yeah.
Yeah, I think all the thermal crosstalk and power related to thermal is also specific to thermal optic. If you change it to add another MEMS phase shifter, all those problems will disappear. Thermal phase shifter, but you have new problem, right?
Yes, exactly. And particularly for like the power consumption, right? The static power consumption, you need to keep on supplying the power to maintain the phase angle. So that is a huge disadvantage of thermoptic phase shifters. And that's where the motivation for pruning comes, that if you can reduce the phase angles, like you do not need a 99% sparsity. If you can reduce the phase angles by 10%, that means a 10% saving in power, which is quite significant.
Yeah, compared to other, non-volatile, at least thermoptic phase shifters is flexible. It's reconfigurable. Okay, another question from robustness point of view. Besides those off-chip pre-deployment optimization techniques, is there any on-chip online method that can help solve robustness issues?
That's a good question. So I think there should be some works on remapping. So, GH, if I'm not wrong, you and your group had some works here, right? On remapping.
Well, yeah, we have some like on-chip training. So instead of doing optimization offline, we can do training online.
Right. So that's a good point. I cannot remember of any methods for on-chip optimization. But yeah, I can take a look. Yeah, good question.
Yeah, remapping is another way. It's more like architecture-wise, right? Remap your workload to your circuits, so you can, to some degree, minimize the error.
Right.
Yeah. Okay, another question. You mentioned the fabrication cost is high for photonics and low for CMOS. But for silicon-photonic chips, does not require advanced technology node. It's 100 nanometer. So it is usually like cheaper to fabricate a silicon-photonic chip compared to like 12 nanometer CMOS. So.
So I think if you compare, let's say 100 nanometer, like 100 nanometer itself, I feel is optimistic for photonics. Like I was mentioning, like MCI sizes are like hundreds of microns, right? So if you compare, let's say, at like 100 micron fabrication cost versus 5 nanometer fabrication cost, so probably at that scale, 100 micron fabrication cost will be cheaper. But then again, the price that you are paying is in terms of area, right? So what my point was that if we keep the technology constant, so let's say if we wanted to fabricate a 100 micron photonic device versus a 100 micron CMOS chips, which will have many transistors, much more complexity, fabricating the CMOS chip will be cheaper compared to, let's say, fabricating 100 micron photonic, like 100 micron purely photonic chip. Now with silicon photonics, you are merging the best of both worlds. So the prices come down a little because you can now use fabrication techniques that like of CMOS, you can map those to silicon photonics. But at the same scale of devices, CMOS devices are cheaper to build simply because they are being built for a long time. So processes are more mature.
Yeah, I can understand the price per device. Definitely CMOS is cheaper, right? Per transistor compared to price per MCI. And also if you're using new material instead of silicon, then the price also goes up.
Right.
Okay, another question is from me. Is there any generic training frame metrics to quickly evaluate the robustness of the photonic neural network? You mentioned some trace-based matrix error, right? T transpose, conjugate transpose P. That one's for the unitary structure, right? To evaluate how close the unitary matrix. So if there are any better generic metrics to quickly tell me how good is the robustness or expressivity of this structure without training that. Because based on my recent observation, sometimes you inject some error to the structure. Okay, you observe the matrix has some error, right? Sometimes the 1% error, sometimes 5% error, and I just train that structure to a specific neural network on a specific task. So the 5% error one sometimes give you a higher accuracy compared to the 1% structure.
Right. So without training, a good question. I think so for robustness, I think you do not need training really. You can just see that I have you can pick up any unitary matrix and you can map it to an MCI array and see how much does the unitary matrix change when you add some deviations, right? But for expressivity over the set of all unitary matrices, I'm not sure if there is any mathematical measure of that.
Yeah, so robustness just tell you how robust is the circuit to noise, but how expressive, how trainable It's unknown, right? So if you want this to have high accuracy, you need the high trainability, expressivity, and generalization, right? And also robustness. 4 things for analog computing. Yeah, I just want to see, is there any smart surrogate metrics can directly help with so-called neural architecture search type of work without training?
Right. So we were thinking of exploring like some kind of distillation where we have a very large network and we distill it to a smaller network and see whether the expressivity of the smaller network can be mapped to the larger network. But again, we did not explore that part. So it's still an open question. So yeah.
If you're based on some smart observation on the face value on the topology, you can quickly classify the robustness and expressivity. It will be much better to do automatic explore, I think. Okay, another question. So talk about the resolution on the deck, right? So how about on the ADC part? For example, quantization on ADC sometimes help to mitigate the noise based on the literature, but also introduce some quantization error. Some prior work also used the time integration in the analog domain to reduce some quantization error. But the integrator's response is also non-ideal. So can you share your insights in the sweet point to balance the output quantization error and the noise-induced error?
Okay, so output quantization error versus noise-induced error.
I think probably if you have like 16-bit ADC, there's no problem on quantization error. So basically, pretty much the context is like you have limited quantization bit width. So how can you smartly choose where to quantize and what's the bit width you want to quantize on the output?
Right. Yeah, I would guess that would be very, very dependent on the network itself. So like particularly for photonic neural networks, I have seen like a large variance in resilience of networks based on the trained weights. So I think it would be difficult to comment on this without having a knowledge of the network. So how large is the network compared to the complexity of the task? So quantization error in particular for like when I take a very simple task like MNIST and when I take a very small network, it seems to be very sensitive to quantization error. But I would guess that as your network becomes more redundant, you can afford a little more quantization error. Now, how does that interact with the noise-induced error? Is a good question. I do not have the answer to that off the top of my mind.
I think indeed it's very related to the structure, right? The noise level. For example, if your circuit is noise-free, then to minimize quantization error, you should have a large enough MZ array, right? 1,000 by 1,000 without error constraint, because that gives you a minimum quantization error. But if the MZ array is super noisy, you don't want to have a super large MZ array. Otherwise, the noise accumulation along the network will be very severe. I think it's very critical to decide where and how often do you want to apply quantization and the bit width.
Particularly for quantization, again, our findings have been that earlier layers are more sensitive to quantization errors. So ideally, you would want more precision given to the earlier layers.
It's also related to ADC speed and power, right? The bit width. And indeed, for different layers, you can have a different customized bit precision if your ADC can support a tunable resolution. Otherwise, it's a fixed. Okay, this one is asked related to pruning. So what's the fundamental technology path to ensure analog computing hardware has device-to-device consistency without harming generality in function? Is it mainly from device or fabrication or circuit design? Can we show? It's
No,
more like a generic to analog computing.
Yeah, I think it's very, very related to architecture. So this is one of the reasons why MCI-based networks are so sensitive to uncertainties, is that like all our experiments, we have considered a flat network, right? So once you have flat networks, you have so many devices and so many things that can go wrong. And all of these cumulatively add up. So I feel that on the device side, really, there is not much more we can do, right? So at the device level, based on my study of existing literature, like 1 to 2% deviation in beam splitter ratios, or like 0.2 radian deviation in the phase shifter angle, you really can't do much better than that. So I think we should accept them as it is and try to build architectures around that. That should be like try to have redundancy built in, try to do smart remapping, try to have like more sensors or monitors, as Alex pointed out, to detect things going wrong early. So like in my opinion, I don't think much better can be done on the device part. It's more about architecture.
Yeah, basically all the layers can help to some degree, right? Better fabrication, better packaging, they can all solve those problems to some degree.
Right.
But the lower the level, the higher the cost. So if you can just do something in the algorithm architecture level, don't do it in the device material level. It takes a super long time. I give you a 10% gain or something. But architecture-wise, you can have a larger room. Yeah.
Right. Exactly.
This one's okay. I think I covered all the questions. Okay. If there are any more questions from the audience, you can unmute yourself or type in the chat box. Okay. Okay, no one asked further questions. Yeah, we can definitely have more offline discussion. We have the Slack channel, and the Slack video will be online soon, I believe. And please share the videos with your friends who cannot attend at this time. So thanks for everyone for joining the seminar, and especially thanks, Sanmitra, for the great talk and sharing your perspective on the robustness issues. And yeah, everyone welcome to subscribe our mail list and follow our future seminar events in the following month. And this concludes our event today. Yeah. Thank you again. Thank you, everyone.
Thank you.